The areas of regular polygons. A regular polygon is a polygon whose side lengths are all congruent and angle measurements are all congruent. In a sense, it's the perfect polygon for whatever number of sides it has. What we want to do here is brainstorm an idea on how we think that we could calculate the area of this figure. Okay, and then we're actually going to do it using a ruler, which means that our answer might not be exact, but we're going to go with it because the practice is good. So if we're thinking about how to calculate the area of the figure, the one really important thing here is that we use perpendiculars. If you don't have any perpendiculars in the figure, then you're going to be multiplying values that you should not be multiplying by. Okay, in addition to that, we've already learned how to calculate the area of a lot of shapes. We know how to calculate the area of rectangles, parallelograms, triangles, trapezoids, kites, and rhombuses. And now we could divide this figure up. I think that's the approach that most of us will think of. We can divide this figure up into those shapes that we've seen. For example, you could draw a line here, which would create a triangle. You could also draw a line here, which would create a triangle that's congruent to the other one, and then you would have a rectangle in the middle, okay? However, the problem with that idea is that you're creating a bunch of different shapes. You're creating a couple of triangles and you're creating a rectangle. And if we have a different figure like a heptagon, that idea really wouldn't work because this point is not above that point. In fact, at the top you would have a vertex. Okay, so we couldn't really use that idea. Instead, what we're going to do is try and choose something that's consistent. And the consistency here is going to be dividing the whole figure into a bunch of triangles that are congruent. For the hexagon, what you're able to do is connect opposite vertices. You could do this for any polygon that has an even number of sides. If you have an odd number of sides like a heptagon or a pentagon, it's a little bit more difficult, but there would be a point in the center where all the segments extending from vertices could meet, and you would end up with 7 or 5 congruent triangles. So in the even-sided figures, it's a little bit easier to do this. Okay, but I do have 6 congruent triangles. Okay, I have 6 congruent triangles here, which means that the area of this is going to be equal to 6 times 1/2 base times height, where the base and the height are referring to any of the triangles that we have here. So let's take a look at one of the triangles. I would typically look at the triangle that's at the bottom, except I don't really have a lot of room to show you the use of my ruler. So I'm going to use another area, which will just be over here. Okay, so the side length is going to be a 5, okay? It appears to be about 5 centimeters, so we'll just let that be. Okay, so 5 centimeters. Now, that would be the base. Okay, so the area is 6 times 1/2 times 5 times the height of the triangle with respect to the 5. Okay, so in this case, I'm just going to eyeball it here. Okay, I'm going to imagine setting up a perpendicular. One thing that you could do is use the little lines that are on here. Take one of the lines that's a little bit longer and try and get that to run right along that side edge. Okay, so it appears that would be a good representative of the height here. And the length of that is about 4.2 centimeters. 4.2 centimeters. All right, so to calculate the area, I would just multiply all those values, which I'm going to go ahead and do here. However, the actual area of this figure is not really what's important. What's important is the idea that we use to get to that answer. But we'll go ahead and look at what it says. All right, so we got 6 times 1/2. That would be the same thing as 3 times 5 times 4.2, which gives us 63. That's interesting. Okay, so this is an approximation because we measured things, of course, but it appears to be 63 centimeters squared. Okay, but what we really want to think about is what all these values would represent with respect to the hexagon, not so much the triangle. The idea works, but if you have any regular polygon, how do these numbers actually apply to that figure? Okay, the 1/2 is just a number, it's a 1/2. So we're gonna keep that. The 6 is gonna refer to the number of triangles that we have in the figure, okay, which is also going to be the number of sides that we have in the figure. It's gonna represent the number of sides that we have, okay? I'm gonna refer to that as n. In fact, I'm gonna write it up here first because some of this is gonna switch orders. Okay, so you got the 1/2, the 6 is gonna represent the number of sides, which we're gonna call n. The 5 is the length of one of the sides. It's the base of the triangle, but it's the length of one of the sides. We're gonna refer to that as s, the side length. All right, and then we have one more variable, which is the height, but that would be the height of the triangle. With respect to the hexagon, in this case, yes, it is half the distance across here. But in other figures like a pentagon or a heptagon, anything that has an odd number of sides, this is not going to be like a half distance of it. Okay, so we're going to give it a new name, something very unique, which is called the apothem. This is the apothem. And we're going to represent that with the letter A. All right, so for calculating the area of any regular polygon, you can take 1/2, the number of sides, times the side length, times the apothem, which is normally going to be printed this way, 1/2 ASN. No particular reason that it's in that order. This is just the way that we write it. For this part of the video, I just want to go over some vocabulary. If you have a regular polygon like this, that being a hexagon again, if you have a regular polygon, you can inscribe it into a circle. That means that there's a circle that goes around it, or you can say that that circle circumscribes the polygon. It's going to make contact with all the vertices as it goes around. Now, the center of that circle, which would be located here, can be connected to two different parts of the polygon. If you connect it straight out to one of the sides, that would be perpendicular there, and it does make contact at a midpoint. If you do that, you get what is called the apothem, and you saw me use that to calculate the area for the other hexagon. That would also be the height of the triangles that you saw. In addition, there's another measurement that you can get from the center, which would be from here out to that corner, and we would call that the radius because that measures out to the edge of the circle that we have. Now, it is also possible, though not very likely that you'll see it, you can inscribe a circle inside of the polygon so that it's tangent at all of the sides that we have. Okay, so it makes contact at the same place where the apothem would on each of those sides. Okay, and we call that circle the incircle. And maybe the most important thing that you can take away from that is the apothem is going to be shorter than the radius. For example, one, we're going to find the area of a regular decagon. A regular decagon, that means it has 10 sides. We're going to find the area of a regular decagon with a side length of 8 and an apothem of length 12.3. Okay, sometimes it's nice to draw pictures, but if you got a decagon, that might be a little bit complicated. What we're going to do is go ahead and just stick to the formula. The area is going to be equal to 1/2 the length of the apothem times the side length times the number of sides that we've got. All right, so in this case, it appears as though we have everything that we need. The area is going to be equal to 1/2. The length of the apothem is 12.3. The side length is going to be an 8. And the number of sides we have, because it's a decagon, is going to be 10. So if we multiply all this together, we'll have the area. All right, now some things you can actually do on your own. 1/2 of 8 is actually just 4. 4 times 10 is going to be 40. So this is the same thing as 40 multiplied by 12.3, just in case that saves a little bit of time. All right, so 40 times 12.3 is going to give us 492. So the area is equal to 492. And units, it appears as though we have not been given any units, so what we can write is u squared, which will just vaguely stand for square units or units squared. Example 2, a regular hexagon has a radius of 5. What is the exact area? Okay, we are not given much information here. We do have a hexagon, which tells us that we've got 6 sides, but we don't know what the length of those sides are, and we don't know what the length of the apothem is, but we are provided the radius. Okay, so let's see how that might work out. Quick sketch of a hexagon, six-sided figure. A decagon, that might be difficult to draw. A hexagon, I think we can come up with a basic picture for it. Okay, the radius is going to extend from a center point out to one of the vertices. Okay, so this could be a radius right here. That could be 5. But you have other radii that you can also draw. There'd be one that would be here as well. Okay, so there's one thing that we do learn right now, which is if we're focusing on the triangle, which is part of how we calculate the area of this, we actually have an isosceles triangle. The apothem is the height of that isosceles triangle. All right, but what else do we know about this triangle? Because just given those two measurements, you can't figure out the apothem or the height of the triangle, and you can't figure out that side length. But remember, it's going to take 6 of these triangles to make the whole thing, right? We could divide that way, we could divide here, here, and here. And all of those triangles would be congruent. And in the middle right here, where they all meet, together they have to make a complete 360 degrees. So if I take 360 degrees and I divide it by 6 triangles, that gives me 60 degrees. The top right here is going to be 60 degrees. And that means that if I just take half of that triangle, let's go ahead and just sketch it separately. That top angle is 30 degrees. See if I can actually make that look like 30. That'll be 30 degrees. You also have a right angle at the bottom coming from here. This would then have to be 60 degrees. So we actually have a 30, 60, 90 triangle with a hypotenuse of 5. And in a 30, 60, 90 triangle, the hypotenuse is going to be twice the length of the short leg, which makes this 2.5. And the longer leg is going to be the length of the short leg times the square root of 3. So this is 2.5 times the square root of 3. Okay, so how does that apply to our actual figure? This is the apothem, and this is actually half of the side length. So the side length is going to be a 5. And in fact, what we have here are actually equilateral triangles. They're not just isosceles, but in a hexagon, they're going to be equilateral. Okay, so let's get to the formula for area. That'll be equal to 1/2 the apothem times the side length times the number of sides. 1/2 is 1/2. The apothem is 2.5 times the square root of 3. And remember, we're doing this as exact area, so we're going to keep that as square root 3. The side length is 5. The number of sides is 6. All right, so let's go ahead and start multiplying this together. The 2.5, that's a little bit odd compared to the rest of them. So I'm going to change that into a fraction. The 2.5 actually came from taking a 5 and dividing it by 2. So let's just write that as 5/2. And let's go ahead and straighten this out too. I think that'll look better. So you have 1/2. Okay, so let's multiply everything but the radical. You're going to have a 5 times a 5 times a 6, which is going to be 25 times 6. So you get 150. You've got 2 times 2, which is a 4. And you still have that square root 3, which can sit on top. 150 is not divisible by 4, but it is divisible by 2. So we can rewrite that part as 75/2 and keep the square root 3, and that is the exact area for the hexagon.
Later, blah.